All right, let's dive right in. Today, we're getting into the heart of pretty much every modern computer, smartphone, you name it. We're going to explore this huge, revolutionary shift from having a single, totally overworked brain to a powerful, coordinated team.
You know, for decades, the story of computing was super simple. Just get faster. Every single year, processors got faster, computers got faster, everything was on this rocket ship of progress. And then, all of a sudden, it just stopped. The race to make a single computer brain run faster and faster hit a dead end. So what happened? What was the deal?
Well, to get the answer, we have to rewind to the early 2000s. This is when engineers ran, like, headfirst into a very real and very, very hot physical wall.
For the longest time, making a computer faster meant only one thing: cranking up the clock speed. Just turning the dial to make one single processor do more stuff every second. But here's the problem. The faster you run a processor, the hotter it gets. And we were really pushing the limits of heat and how much power these things were sucking down. We literally couldn't make them faster without them melting. Okay, to make this super clear, just picture a kitchen with one master chef. The performance of a single-core processor is basically how fast that one chef can chop vegetables. For years, our only solution was just to train that chef to chop faster and faster and faster. But you know, eventually, no matter how good they are, one person can only move so quickly. You hit a human limit, or in this case, a physical one.
So, with that single chef approach totally maxed out, the entire industry had to come up with a whole new recipe for performance. If you can't make your one chef any faster, what on earth do you do? Well, the answer literally changed computing forever. You hire more chefs. That was the big idea. Instead of one super-fast, completely overworked processor, the industry shifted to using a whole team of several more efficient processors, or cores, all working together on the same chip. And just like that, the multi-core processor was born. So, the big question is, did it work? Oh yeah. The source material shows that just by adding a second core, a second chef in our kitchen, you could get a speedup of up to 1.75 times on certain jobs. That's a huge jump. The power of teamwork was just undeniable. But, and this is a big but, there's a catch. Just putting 4 chefs in a kitchen doesn't mean a meal gets made 4 times faster. You need a plan, a recipe, you need a head chef calling the shots. You have to actually teach the hardware how to work together. And that's a software problem. And this is where this really clever piece of software called a compiler steps in. You can think of it as the master head chef. It looks at the whole program, the recipe, and it figures out which tasks can be done at the same time. For instance, the source points out that it can look at a really repetitive task, something programmers call a loop, and see if each little part of that task can be done on its own without waiting for the previous one to finish. So the compiler's job really boils down to 3 key things. First, it reads the whole recipe. Then it identifies all the things that can happen at the same time. You know, like one chef can be chopping onions while another is peeling potatoes. And finally, it writes out brand new instructions, assigning these different jobs to the different cores, our team of chefs. Now, this gets even more efficient with a cool technique called SIMD. Imagine the head chef doesn't have to go to each cook one by one. Instead, they can just yell one command, "Everyone, chop!" And the entire team of chefs start chopping their own pile of vegetables at the exact same time. That's SIMD, one single instruction acting on tons of different pieces of data all at once. It's incredibly powerful. So how do we actually get this parallel magic to happen? Well, there are 2 main ways. The explicit path is kind of like a programmer writing a recipe that's specifically for a team of chefs, telling them exactly what to do from the start. But the inferred path, that's where the real magic is. That's where that genius compiler acts like an amazing head chef, automatically figuring out how to split up a recipe that was originally written for just one person. Okay, so we've hired our team of chefs, we've got a head chef giving them a plan to work together. Problem solved, right? Well, not quite. Turns out, in solving one bottleneck, we accidentally created a brand new one. To get this new problem, let's go back to our kitchen's pantry. That pantry represents the computer's main memory. Every single chef needs to get ingredients from it. The time it takes for one chef to walk to the pantry and come back, that's latency. And how many ingredients they can carry in one trip, that's bandwidth. Now, when you have a whole team working at once, you can probably see where this is going. Yeah, Imagine having 4 or 8 or even 16 chefs all trying to get into that one pantry door at the exact same time. It's a disaster. You get a massive traffic jam. All of our shiny new cores were trying to grab data from the same place, creating this huge bottleneck that just slowed the whole kitchen down. The solution to this was, honestly, brilliant. They decided to give each chef their own little mini fridge or prep station right next to them. This is what cache memory is. It's a small, incredibly fast bit of memory right next to each core that stores the most common ingredients, so the chefs don't have to keep making that long trip back to the main pantry.
And that's the magic of cache. By giving each chef their most used ingredients right at their own station, it just wipes out all those slow, constant trips to the main pantry. This dramatically cuts down on the delays, and it lets the whole team work at full blast without ever stepping on each other's toes. So, we've gone from clock speeds to multiple cores to compilers to caches. It's a lot of techie stuff, I know. But why does any of this matter to you, right now, in your daily life? Because pretty much every single amazing piece of technology that defines our world today is built on this foundation. I'm talking about the artificial intelligence that powers chatbots, the absolutely stunning graphics in your video games, complex scientific models that predict climate change, analyzing huge amounts of data. None of that would even be remotely possible without computers learning how to work as a team. So you see, the race for the fastest computer didn't really stop. It just completely changed directions. Instead of trying to build one impossibly fast sprinter, we figured out how to build a perfectly synchronized, incredibly powerful relay team. And that single shift has changed absolutely everything. Which brings us to a final thought. We solved the processor wall, we solved the memory bottleneck, all by learning how to work in parallel. But technology, as we know, never stands still. So what do you think is the next great challenge? What's the next big wall that we're all going to have to figure out how to climb in the world of computing? Thanks for tuning in.